Hello, welcome to a new topic in physics. This time it's magnetic fields. Follows on directly from electric fields, so will be somewhat similar but will be different. And this one's just going to be the introduction. So let's just quickly go through some applications of magnetic fields, just so for you to get a feel of the fact that physics is real. It is out there, and what we're learning does actually relate to the real world, because that's important. Now these videotapes, pretty old, a bit of a dated technology, being replaced by hard drive recorders now, but these were very reliant on magnetic fields. We're a classic example of using magnetic fields to record data, but computer disks do a very similar process, and we'll be looking at most of these in a bit more detail later on. Levitation trains, we don't have any in Australia, but other countries are building them. Basically what they use is the repulsion of magnetic fields to lift the train up off the rails and give it a frictionless ride, a very smooth but frictionless ride. So because you don't have any rolling friction, you lose a lot less energy, they can go faster. Pretty interesting technology, and people are building them around the world. Biomagnetism, that's when animals use magnetism for various reasons. The main one they use it for is for navigation. These turtles, they swim across the oceans, the Pacific and the Atlantic Oceans and all over the place. They travel huge kilometres in a year. But amazing thing is that they always go back to the beach that they were born on, where they hatched, to lay their eggs. And so they return. And people have been mystified as to how they can actually do this, and it's a combination between the lunar cycles, stars, but they also use the magnetic field. They have a way of memorizing the variations in the magnetic field, which are way beyond human perception. And this is a little experiment just showing how this turtle lines itself up to the magnetic field. We'll go into that in a bit more detail later on, and most of these applications will actually look in a lot more detail as we go through, so I will rush through them a little bit. Auroras, the northern and the southern lights. Here in Tasmania you might be very lucky to see them, but if you go certain parts in the northern hemisphere or down to Antarctica, you see these fantastic lights, and they're very much related to magnetic fields. Security cards, those little black strips on your credit cards and security cards and things, are all reliant on magnetic fields to store data. Geomagnetism, where would we be without learning a little bit of geology? And so we're going to relate how magnetism in rocks can tell us a lot about the Earth. There's a thing called a magnetohydrodynamic drive, and this boat is being powered by that. It's using magnetic fields to push water through. Magnetic mines, of course, application. We won't need to look much into those because pretty straightforward how they work. They just sense the magnetic field from the boat and set themselves off. Speakers, we're going to learn a lot about how speakers work and how they're an application of magnetic fields. DC motors, we're also going to examine very simple motors like this and work out how they work. We're also going to try and make our own DC motors in class. Mass spectrometers, we talked about these in electric fields, but we're also going to look at how magnetic fields relate to them. MRI, magnetic resonance imagery, very effective at looking at soft tissue like the brain here and the eyeballs, much better than X-rays. We'll look at how these work and how we get fantastic images from the application of some pretty high-powered physics. And of course there's toys. Here's a little globe levitating because of magnetism, and we'll look at some of those as well. So let's move in. Oh, one last thing. You could have a magnetic bed. This is pretty cool. It's a bed that actually hovers above the floor. There's no connection, so it's supposed to give you a very nice sleep. There's another picture here, all made up, but it's only a cool $1.5 million because the technology to make that happen is pretty advanced, and so not many have been purchased at that price. But if I had a spare 1.5 million, I might think about putting one in. So let's get into our basic theory, working out what a magnet is, some defining things. Now any magnet will have a north or a south end, and the north end is referred to as the north end because it's a north-seeking. It always points towards the geographic north, and the south is a south-seeking end. So if you put a bar magnet, tie a loop of cotton around it and let it swing freely, it will always align itself to the Earth's magnetic field, and so have a north and a south. And that's what the earliest compasses were. The Chinese discovered that there was a mineral called magnetite, and if you had a rock that contained a fair amount of magnetite, you could have a lump of that rock, put it on a piece of wood, then float it in a bucket of water, and that piece of rock will always align itself in the same orientation relative to the Earth. And that was the earliest compasses, were just these lumps of magnetite. And the Chinese used them to navigate around all the Asian areas, and then they refined them into metallic objects and dragons shapes and things like that, and they were the earliest compasses. And if we want to do a little bit of history, we would know that it was Marco Polo who went from Europe to China, and one of the things, and then he went back and he brought back all these technologies that Europeans didn't have, and one of those technologies was, of course, compasses, and that allowed all the European nations to then sail around the world without falling off the edge, because they sort of knew where they were going. Plus there was a whole lot of other discoveries as well that helped. Okay, so that's your basic compass, and that's what works with if you have an orienteering compass or something like that. Instead of a piece of string, it's just floating on a needle point. Now, we should have all played with magnets in some stage of our life, hopefully, but if you haven't, don't worry, we'll bring some bar magnets into the classroom and we'll have a play with them. And we should have discovered that like poles repel, so here's two souths and they want to push each other apart, and you can actually feel the force of repulsion even though they're not touching. It's like an invisible force. But it is a physics force, and unlike poles, attract each other. Here's a north and a south, and we'll be able to play with that as well. Now, what happens when you break a magnet apart? This is a very interesting question that physicists have been pondering for many years and haven't quite come up with a 100% answer yet. We do know, though, that if you break a magnet, you get two magnets, each with a north and south, and you break it again, you get two more with a north and a south. So theoretically you could keep doing that right down to the atomic scale, but what happens? Where does the north go and where does the south go? And some people have postulated that you must have something that's called a monopole, which is just a north without a south, or just a south without a north. No one's found them, people are looking for them, think about them, they're theoretical, would be very interesting, be great use in computing, but basically are purely theoretical at this point in time. So how does magnetism work? Well, we use the theory called domain theory to explain why some objects are magnetic and other objects aren't magnetic, and how we can make some objects magnetic, and then when we take away a magnetic field they don't keep being magnetic. And the domain theory basically says that if we look at something that can be magnetic, be it permanently or temporarily, it's made up of little domains, and these little domains are thought of as little bar magnets, little mini magnets. And so a bar magnet would be made up of lots of mini magnets combined. Each of those mini magnets is referred to as a domain. And so what happens is, if you have a lump of steel, these crystalline, if we go back to physical science, the crystals that make up the metal would all have their own alignments, and therefore these domains would all cancel each other out. But if we heated this up and then put it in the presence of a magnetic field, all the little bar magnets, all the crystals will realign themselves and allow themselves to realign, and you would get a consistent alignment of the domains, and therefore this would be strongly magnetic. And as we let it cool, this arrangement would stay as distinct from this arrangement, and that would be our permanent bar magnet. Alright, now we're also going to introduce you with some things that are only magnetic whilst they're in the presence of a magnetic field. Things like, I would refer to them as the soft metal cores in solenoids and electromagnets. And what happens with these guys is, let's get my pen, they start off like this with no magnetic field. We put them in the presence of a strong magnetic field and they align themselves like that, and so they act magnetically. But then when we turn off the magnetic field, they revert back to this, and so they don't have any residual magnetism. And things like the iron filings that we use in class will be like that as well. Now, what are these domains? Well, in reality, if we brought it right down to a very small scale, these domains are electrons. Each electron is spinning on an axis and it produces a north pole and a south pole because it's got a charge, and that charge, because it's moving, generates a magnetic field. But we'll learn a little bit more about that later when we do a bit more physics. So here's just another diagram. This would be our bar magnet before it's made put into a strong magnetic field when it's warm, and this is our bar magnet afterwards. Now we've got a nice strong, we've got a north and we've got a south there. And this is what it looks like. If we take a piece of metal, polish it and throw it under an electron microscope, these are 20 micrometers, so very small. Can't see atoms at that scale, but we can see the domains. And this is what they look like on other things as well. And on videotapes, this is a blank videotape with no recording. This is what it looks like when it's been recorded and we've aligned all the little pieces, little bar magnets, little pieces of iron filings and other substances in the tape, and we align them, and so we create domains, and this is digital data. On a hard drive, the digital data is recorded as these domains, much smaller scale, therefore we can store much more data on them, and that's why videotapes have been replaced by hard drives. So in the next video we're going to learn how to actually draw magnetic fields, what they look like and how to draw them. Alright, so cheerio!